right, we're going to do a little more graphing of quadratics. We're not solving quadratic equations with graphing. This time we're just kind of doing straight up graphing. We're learning how to take that parent function and move it around and make it bigger and smaller and all the things. So let's dive in. So first up here, my head in the way, is just reminding us what that quadratic parent, because we're going to compare all of these transformations to the parent, because that's a great way to understand what's happening. So our first type of transformation that we can do is we can do a vertical translation. So the part that changes the parent function is if we add or subtract a number outside of the parentheses. You'll see what I mean by parentheses in a second. So if we add something to the end or subtract something from the end, then it either moves the graph up or down. Now, if k is positive, it moves it up, which makes sense, right? If k is negative, it moves it down, which also makes sense. We got a couple little examples here. We've got this h of x, which is x squared plus 2, so it all shifted up 2. Now, I also noted you notice on the parent function, I noted a few of the points. And the one that I kind of want you to zero in on is this 1, 1 and negative 1, 1. Those are kind of our anchoring points, right? It's because that's how much it opens up, just the parent function there. Now, if we pull up this guy, you notice that it's still on this h of x, it still goes up, it goes over 1 and up 1 over 1, right? From the new vertex. So it didn't change how stretched it is or compressed it is or anything else. It didn't change the shape. It just took that parent function and it shifted it up 2 units in this particular example. And then this m of x, it moved it down 5 units. But you still notice that it goes up 1 over 1 on both of these things, up 1, back 1, right? So it's the same idea. So that is a vertical translation. What about a horizontal translation? Well, that looks like this. So you notice I said inside parentheses. So we've got adding or subtracting something outside of the squared and then something inside of the squared. And this is I want to note and want to kind of make a big deal of this, because the more you understand this, the better off you're going to be. Because in Algebra 2, we're going to learn how to graph all kinds of things. And you're going to find that once you kind of learn this pattern that we're learning today in this lesson, you can apply it to pretty much any function, and it's going to work the exact same way. And so inside parentheses, and this is what I want you to remember one thing I want you to remember for this is inside the parentheses, it moves opposite expectation. Okay? Opposite expectation. Right? So if h is positive, it's going to move to the left. If h is negative, it's going to move to the right. Now, why does it do that? It's because it's negative, and it actually is kind of how squares work and all those kind of things. But inside parentheses, and this applies to like a whole bunch of different kinds of functions. Inside the parentheses, and later we'll learn some functions that are parentheses, like square roots and things like that. But almost always inside parentheses, it moves opposite expectation, right? So this example of a to the x, or a of x, not a to the x, a of x, we've got x plus 4 inside parentheses squared, and that moves to the left, even though it's positive, right? And the negatives are going this way, but this moves our graph 4 over. Now, you notice, again, just like our vertical translations, these, we still go up 1 over 1 and up 1 back 1 to get that reference point and everything else. So it's just shifting left and right. It didn't change the stretch or the compression. We'll talk about that in a minute. So that is that. Let's do a little example here. Let me move all this for a minute. All right. So we want to describe how the graph of each function is related to the graph of the parent function. So this one, where does it shift? Well, we've got both horizontal and vertical shift. So it shifts or translates, you could use that word as well, shifts 2 up and 3 to the, that's all smashed together, to the right, not left, right? Because inside the parentheses, it moves opposite. So this would shift our parent function up 2 and to the right 3, right? So that's how this one right here works. What about this one? So in here, it's going to, we'll use that other word, it's going to translate 1 down and 3 to the left, right? Because it's opposite in there. And then I like to put it in symbols too, just because it's easy for reference later. So it shifted down. That's a weird looking arrow. Down 1 and to the left 3, right? There we go. So what about those stretches and compressions? Let me pop these back on there, right? So we've got an a. So if we multiply something times that x squared, then it's going to either dilate it, it's going to either get bigger or smaller, or it's going to reflect it. Now, so there's more to this. It's a little bit more confusing other than the opposite inside parentheses bit, right? It's just a little bit more confusing, but it's not that bad. Let's kind of talk through the puzzle pieces, right? So if this number is less than 0, so in other words, if it's negative, then it reflects it. Now, you notice we have an example doing that, and I have kind of an intermediate step here. This one right here, this g of x that I added, in this case is just a negative x squared. So it's just taking the parent function and flipping it down, right? So that negative on there flips it down. In this other example, it flips it down. We'll talk through the examples in just a second. If the absolute value of a is greater than 1, so if it's 2, 5, 25, or -2, -5, -25, the negative is going to flip it down. But those numbers are going to vertically stretch it. Now, this is important, and I've been saying this with my hands and all the way through so far, and you have to think up and down. That's where this particular topic gets a little bit confusing, because when we vertically compress, it looks like that the thing gets bigger, and it does horizontally, but it gets pushed down lower, right? And so when it's between 0 and 1, so if it's a fraction like 1/2 or 2/3 or 5/9 or whatever it is, it's going to vertically compress. If it is 2, 25, 88, whatever, it's going to vertically stretch. So it's going to get narrower horizontally, but it's reaching up to the sky, or it's pulling down, right? And so that's how you want to think about this. So for our couple of examples here, this one, this y of x, is this guy up here. So you see, compared to the parent, he vertically stretches. Now, how much does he vertically stretch? Well, he vertically stretches by 3. So it was at 1, 1, and now that kind of new reference point, that beginning sort of point we're talking about, is now at 1, 3, right? It's just going to be 3 times whatever it was. So like this point, that if it was shifted up, it was originally at 4, so it would be 3 times that. So it's actually going to end up being up at 12, which is up off the screen and things, right? So it's just going to be 3 times whatever it was, right? Now for this one, I combined 2 things in one just for the sake of neatness. Now I did add this reference for the negative to see what that would look like, so we can compare these two. So comparing just to the reflected parent, right? So you can see that it vertically compressed, right? It got smooshed towards that x-axis, right? I know it's a little bit confusing because it looks wider, and it is wider, but it's vertically compressed, right? So that's the fraction there, right? How much was it compressed? Well, it was compressed by half. So our new reference, like this new reference, is going to be at it's negative 1/2, but 1 negative 1/2 and negative 1 negative 1/2. So it's half as big. So like this point right here, this one normally is at 4, so now it's smooshed up to 2, which is half of 4, right? Now, and we don't usually draw them because it doesn't usually fit on the size of graph that I draw, but the next point would be, the next on the parent would be 3 and 9, because 3 squared is 9, right? And And so 9, half of 9 is 4.5. So it's going to shift up to negative 4.5 because of this negative here. Right? So it shifts up to negative 4.5. We even get to see the fourth one, because 4 squared is 16. Half of 16 is 8. So it shifts everything down by a half. So that's what happens when we do dilation and reflection. The negative is the reflection, and the number itself without the sign is how much it's dilated by. All right. So, let's kill off all that stuff. So all of those combine together to make up what is known as vertex form. So I'm not going to relabel all these. You have that in your notes from what you saw there. So the A is the one that does the dilation. The H is a horizontal translation. Remember, it goes opposite of what you'd expect direction-wise. If it's positive, it goes to the left. If it is negative, it goes to the right, right? And then K goes the same way we'd expect. So positive, it goes up. Negative, it goes down. This is a vertical translation. The actual vertex of the parabola, this is why this is called vertex form, because H and K give you the vertex, right? Now, H is the opposite sign. So if it's plus whatever, then it's going to be negative here. If it's minus whatever, it's going to be positive here, right? So, but these two numbers extracted from there give us the vertex. This is a very, very useful form. Not so useful if we're wanting to find like zeros or something, but for a lot of other things, it's very useful to get a quick picture of what the graph is going to look like. Let's do one more example, and then we're going to be done. So, now, you notice there's no graph here. We're trying to get an equation. We're going to do it based on the things that we've learned. So write a quadratic function in vertex and standard form. So we're going to have to do a little algebra manipulation to change between forms. It's not going to be too bad. Don't stress. That contains this point and the vertex of this. So where are we going to start? We're going to kind of start a lot like when we were way back and we were finding linear equations and linear functions, and we would plug a point in order to find that b, right? We did that lots back in the day. We're going to kind of do the same thing. So that vertex form is f of x equals a times x minus h squared, I almost said plus b, plus k. Right? So that's the vertex form. So let's plug in some things that we know. We're going to hold off on this point for a second. But from the vertex, that gives us h and it gives us k, right? So just from the vertex, we know f of x equals a times x minus 2. So you see the sign switched, right? From positive to minus, right? And then plus 4. So how could what do we need to do in order to get to vertex form? What do we not have? Well, we don't have a. How could we do that? We can do it exactly like we did, just like what I just said. We were trying to get slope-intercept form of a line. We can take and plug this point in and then solve for a. So that's exactly what we're going to do. We're going to change this to the y part of that point, and we're going to change this to the x part of that point. Plus 4. So let's plug in this point. So we're going to put the 6 where the y is and the 3 where the x is. Now let's go and solve for a. I think I'm going to switch to just using y. I feel like that green is a little bit hard to see on here as a maiden color. So 6 equals a. 3 minus 2 is 1 squared plus 4. 1 squared is 1. So 6 equals a minus 4. We get rid of this 4, so we need to add it to both sides. Plus 4. So a equals 10. So this equation in vertex form is f of x, excuse me, equals 10. I thought 10 seemed a little bit weird. Did you catch my mistake already? I paused because I thought I made a mistake, and I did, in fact, make a mistake. Somehow, from this line to this line, this plus 4 changed to a minus 4. I don't really know exactly what happened. So what we would actually do is subtract 4, which would, of course, give us a equals 2. That seems a little more reasonable based on these numbers and all of those things. So f of x equals 2 times x minus 2 squared plus 4. So that is vertex form. That's part of our answer, but we also need to find standard form. So what we need to do is we need to get rid of this stuff here. So I'm going to go ahead and rewrite this as f of x equals 2. But I'm going to rewrite this as x minus 2 times x minus 2. Now, we could use the shortcut here, but I'm just going to reinforce the idea that this x squared, this would not just be this squared and this squared in a thing, right? Because we've got all this that we've got to FOIL out, we've got to distribute it, and all of those things, because I don't want us making those little mistakes, right? So let's distribute x times x, x times 2, negative 2 times x, and negative 2 times negative 2. What's going to happen with this 2? He's just going to come down, right? He's just going to hang out until we deal with him, right? F of x equals 2 times, now it's important that we put this in parentheses because this 2 is multiplied times all of this stuff, right? And so if we don't put it in parentheses, we're going to forget, and we're going to just multiply times the first term here, right? But it's going to be multiplied times everything. So x times x is x squared. X times negative 2 is negative 2x. Negative 2 times x is negative 2x. You may be remembering the shortcut at this point, which would be fine. Negative 2 times negative 2 is plus 4. I'm going to bring down this plus 4. Don't forget it. It'll be easy to do on this one because we're like, oh, we already had plus 4. But that's the inside one from negative 2 times negative 2. We got to bring down that plus 4, right? We've got some like terms here. And so we've got f of x equals 2 times x squared. Negative 2x minus 2x, negative 2 plus negative 2 is negative 4. Don't forget the x. Bring down plus 4 here. Bring down plus 4 on the outside. Now we've got to distribute that 2 onto everything. Right? And so f of x equals 2 times x squared is 2 times x squared. 2 times negative 4x is negative 8x. 2 times 4 is 8. Bring down the plus 4. We don't need those parentheses anymore. Do we have any like terms? Yes, in fact, we do. So our final answer for standard form is f of x equals 2x squared minus 8x plus 12. There it is, and that's it for that lesson. We'll see you in the next one. We're going to do some straight up algebra without doing any graphing in the next one. Yay, it's going to be great. See you there. Bye-bye.